Good morning, students. Welcome back to session 10 of Hilbert spaces. So we will continue the same projections on Hilbert spaces in this class also. So let us take up the first result. So here, if P is a projection on a closed linear subspace M of a Hilbert space H, then X is an element of M if and only if P of X is equal to X, if and only if norm of P of X is equal to norm of X. It's a very simple result. So first we prove X belongs to M if and only if P of X is equal to X. Suppose P of X is equal to X. P of X is equal to X means by definition X belongs to range of P. But range of P is nothing but M, because P is a projection on M means the range of P is M. So this means X belongs to range of P, that's equal to M, implies X belongs to M. So we have assumed that P of X is equal to X and we have shown that X belongs to M. Conversely, suppose that X belongs to M. Now X belongs to M means X belongs to the range of P. Range of P means, say let P of X is equal to Y. This implies P of X is equal to P of Y. So this implies P square of X is equal to P of Y. So P square is P itself because P is a projection. So P of X is equal to P of Y. This implies P of X minus Y is equal to 0. Now P of X minus Y is equal to 0 means X minus Y is an element of null space of P. So now what is the null space of P? Null space of P is nothing but orthogonal complement of M, which is M perp. Means X minus Y belongs to M perp. So let us take X minus Y is equal to Z, where Z is an element of M perp. This implies what? X is equal to Y plus Z. Now Y is equal to P of X. Okay. Now we have taken Y is equal to P of X, implies what? Y is in the range of P. That is, Y belongs to M. Thus, we have expressed X as the element Y plus Z, where Y belongs to M and Z belongs to M perp. But we know that, but X belongs to M. Okay, so we can write X now. Look here, X can be written as Y plus Z, where Y belongs to M, Z belongs to M perp. But X belongs to M. Okay, therefore what will happen? So we can write X can be written as X is equal to X plus 0, where X belongs to M and 0 belongs to M perp. But H is the direct sum of M and M perp. Therefore what we must have? We must have, according to this, Y must be equal to X and Z must be equal to 0. Y must be equal to X and Z must be equal to 0. Therefore what will happen? Say we have shown that, say X belongs to M. Okay, understand now? So X is equal to Y plus Z. Yes, X belongs to M. Now we shall prove that now P of X is equal to X if and only if norm of P of X is equal to norm of X. So first, if P of X is equal to X, what will happen? If P of X is equal to X, then norm of P of X is equal to norm of X. It's straightforward. So conversely, suppose that norm of P of X is equal to norm of X. We show that P of X is equal to X. Consider norm of X square. Norm of X square can be written as norm of P of X plus I minus P of X whole square, because if you expand this, you get norm of X square only. So you call by this number 1. Now P of X is an element of M. It belongs to the range of M and P is a projection on M, implies, in the last class we have shown that I minus P is a projection on the orthogonal complement, which is M perp. Therefore I minus P of X, where it lies? It belongs to M perp. Therefore P of X and I minus P of X are orthogonal vectors. Orthogonal vectors means I can use the parallel as perpendicular identity. So this is equal to norm of P of X plus I minus P of X whole square is equal to what? Norm of P of X square plus I minus P of X whole square, because norm of X plus Y whole square is norm of X square plus norm of Y square accordingly. So from 1 and 2 we can state that norm of X square is equal to norm of P of X square plus I minus P of X whole square. So this is equal to norm of P of X is nothing but P of X is equal to X. Okay, P of X is equal to X. Therefore this implies norm of I minus P of X whole square is equal to 0, or norm of I minus P of X is 0, or I minus P of X itself is 0, or P of X is equal to X. P of X is equal to x. Understand this? So we have shown p of x is equal to x and assuming norm of p of x is equal to norm of x. This is one result. Next, let us take up the other theorem. So if P is a projection on a Hilbert space H, then first one, P is non-negative operator, that is P is non-negative, and 0 less than or equal to P less than or equal to I. So norm of P of x is less than or equal to norm of x for every x in H, and norm of P itself is less than or equal to 1. Okay, these are the four conditions we need to prove. So first one, so let P be a projection on H, which implies P is idempotent and it is self-adjoint, P star equal to P. Now let M be the range of P. First one, let us prove first one. Say let X belongs to H be arbitrary. Then by definition inner product of P of x comma x is this is equal to P of x is P square of x. So P of x comma x. So this can be written as, look here, P of x, okay, or in other words this can be written as P of x belongs to range of P, means P of x is equal to x implies P of x is equal to P of x, so that we written here. So P of x comma P star of x, this is equal to P of x comma P star of x is P of x itself. Therefore this is norm of P of x whole square, but norm of x is always non-negative, thus P of x comma P of x is non-negative for every x, means what? You can declare that P itself is non-negative. Okay. Next, so let us take up the second condition. Okay. Now, so suppose P is a projection, as P is a projection on H, I minus P is also a projection on H. Okay. With range P is a projection with range M, means I minus P is a projection with range M per. We know this. Therefore, by part 1, what will happen? Okay, if P is a I minus P is a projection on H, means I minus P is also non-negative. So I minus P is non-negative. This implies P is less than or equal to what? If you transform this to P here, P is less than or equal to I. But P is always non-negative. Therefore, P lies between 0 less than or equal to P less than or equal to I. This is 2. Okay, let us prove 3 now. Say, suppose x be any vector in H. Now we know that if M is the range of P, then M perp is the range of I minus P. M perp is the range of I minus P. Now P of x definitely belongs to M because P is a mapping from S, H to H. So and M is the range. Therefore now P of x belongs to M and I minus P of x belongs to M perp. Therefore P of x and I minus P of x are orthogonal vectors. So using Pythagorean theorem, we have norm of P of x plus I minus P of x whole square is equal to norm of P of x square plus I minus P of x square. So this is equal to, as this simplifying it gives norm of x square is equal to norm of P of x square plus I minus P of x whole square. But norm of P of x is equal to norm of x. So this implies what will happen? Norm of x square is greater than or equal to norm of P of x whole square. Okay, definitely this is equal to this. See here, this is equal to this plus this, means definitely this is greater than or equal to this and this is greater than or equal to this also. I take a norm of x is greater than or equal to norm of P of x square, or P of x is less than or equal to norm of x, which is 3. Okay, this holds for every x belongs to H. Let us prove fourth one. We have norm of P is equal to what? Supremum of norm of P of x, such that norm of x is less than or equal to 1. By part 3, according to this, norm of P of x is less than or equal to norm of x for every x belongs to H. Therefore, norm of P becomes supremum of norm of P of x instead of norm of P of x. So this is equal to norm of x. So norm of x such that norm of x is less than or equal to 1 means what? What is the maximum value? This is 1. So this is less than or equal to 1 implies norm of P is less than or equal to 1. Norm of P is less than or equal to 1. So we have proved 4 conditions. If P is a projection on H, then P is non-negative and P is less than or equal to 0 is less than or equal to P less than or equal to I. Norm of P of x is less than or equal to norm of x and norm of P is less than or equal to 1. Okay. So now reducibility. Suppose T is an operator on a Hilbert space H. If M is a closed linear subspace of H, then t is said to be reduced by m if both m and m perb are invariant under T. You observe this. If T is an operator on a Hilbert space H and if M is a closed linear subspace of H, then we say T is reduced by M, means if both M and M perb are invariant under T. That means T of M is contained in M, T of M perb is also contained in M perb. So, if T is reduced by M, then we sometimes call it as M reduces T. M reduces T or T is reduced by M. Both are the same. Okay. So, this result says a closed linear subspace M of Hilbert space H reduces an operator T if and only if M is invariant under both T and T star. Observe this, a closed linear subspace M of Hilbert space H reduces an operator T if and only if M is invariant under both T and T star. Okay. Now, suppose M reduces T. M reduces T means then by definition M is T of M is contained in M and T of M perb is also contained in M perb because M and M perb are invariant under T. Okay. So, now we know that a closed linear subspace M of Hilbert space H is invariant under an operator T if and only if M perb is invariant under T star. This result we already proved. Okay. If M is invariant under T, then its orthogonal complement is invariant under T star. Therefore, by the above result, now according to this M perb is invariant under T. According to this, M perb is invariant under T means what? M perb whole perb, that's equal to M is invariant under T star. That means M is invariant under T, M is invariant under T and M is also invariant under T star. Thus, M is invariant under both T and T star, which is the required thing. Okay. Conversely, suppose that M is invariant under both T and T star. Okay. Now, since M is invariant under T star, again by the above, M perb is invariant under T star whole star means T, means M perb is invariant under T. Now, M is invariant under T, M perb is invariant under T means M reduces T. Okay. Then by definition, M reduces an operator T. Next result. So, suppose P is a projection on a closed linear subspace M of a Hilbert space H. Then M is invariant under an operator T if and only if T into P is equal to PTP. Okay. So, if P is a projection on a closed linear subspace M of a Hilbert space H, then M is invariant under operator T if and only if TP is equal to PTP. Okay. First, suppose M is invariant under T. Now, let x belongs to H be arbitrary, then by definition P of x belongs to M, which is the range of P. But M is invariant under T means T of P of x also belongs to M, because T of M is contained in M means P of x is an element of M, therefore T of P of x belongs to M. This implies T of P of x belongs to M means what will happen? P of TPX is equal to TPX. Okay. Look here, T of P of x means TPX. Say T, this implies TPX belongs to M. TPX belongs to M means M is the range of P. Range of P, how the elements in range of P looks? They are looks like P of x is equal to x. So, according to this, P of this is x is equal to x. P of TPX is equal to TPX. This implies PTP of x is equal to TP of x, or PTP is equal to T into P for every x. So, we have proved. We have assumed that M is invariant under T and we have proved TP is equal to PTP. Conversely, suppose that PTP is equal to T into P. Let x belongs to M be arbitrary. Then by definition again P of x is equal to x because M is the range of P. This implies you apply T. T of P of x is equal to T into x. TP is can be written as, just now we have proved, PTP. PTP of x is equal to PTP of x is equal to PT of x. Okay, I apply P on both sides. This implies pt of x is equal to p into t of x, that can be written as t of x itself. Okay, so this is equal to, this implies ptp of x is equal to tp of x, t of x is equal to tp of x. So but m is the range of p, therefore p of tp of x is equal to tp of x, implies tp of x belongs to what? Tp of x belongs to m. Tp of x belongs to m implies Tp of x is equal to that is nothing but t of x. T of x belongs to m. Thus x belongs to m implies, T of x belongs to m. Therefore what you can say, m is invariant under T. Thus m is invariant under T if and only if Tp is equal to Ptp. Next one, if P is a projection on a closed linear subspace M of Hilbert space H, then M reduces an operator if and only if, then M reduces an operator T if and only if Tp is equal to Pt, means P and T commutes. Now let us take, now M reduces T if and only if, by definition M is invariant under both T and T star. This is been taken as a definition itself because this been proved now, just now, previous results. Okay, M reduces T if and only if M is invariant under both T and T star. Now M is invariant under T means Tp is equal to, yes, M is invariant under T means what? We have proved Tp is equal to Ptp, or if and only if Tp is equal to Ptp, you write. And M is invariant under T star means, according to theorem, T star of P is equal to P into T star P. So you take adjoint of this, T star P whole star is equal to P T star P whole star. So this can be written as P star into T, because this reverses, AB whole star is B star into A star. So accordingly this becomes P star into T star whole star is T, that's equal to P star, T star whole star is T, P star again. So this implies Tp is equal to Ptp, and this P star is P because P is a projection, P into T is equal to P, again P star is P, Ptp. So Tp is therefore if and only if Tp is equal to Ptp and Pt is equal to Ptp. Thus what you have assumed, M reduces T if and only if Tp is equal to Ptp and Pt is equal to Ptp. Okay, so you call by this number 1. Now let us take up the result. First suppose M reduces T. M reduces T means just now we have shown Tp is equal to Ptp and Pt is equal to Ptp. Therefore what you can declare, right hand side are same, therefore Tp is equal to Pt. Okay. Conversely, suppose Pt is equal to Tp. This implies what? You apply P on the right. So Ptp is equal to T into P is P square, but P square is P itself, P because P is a projection. This is equal to T into P. Similarly, Tp is equal to Pt implies you apply P on the left. This becomes Ptp is equal to P square T, that is equal to P into T. So call by this number 3. Therefore from 1, 2 and 3 we can say M reduces an operator T. Okay. So M reduces an operator T because M reduces an operator T if and only if this condition already proved. Then by 1 what will happen? Then by 1 M reduces an operator T. Okay. Last result of this class. So suppose M and N are closed linear subspaces of a Hilbert space H, and P and Q are projections on M and N respectively. Then M is orthogonal to N if and only if P into Q is 0, if and only if Q into P is 0. Okay, right. Since P and Q are projections on a Hilbert space H, by definition P star is P, P square is equal to P, and Q star is Q, and Q square is also Q. So now PQ is 0 if and only if what will happen? PQ whole star is equal to 0 star, if and only if PQ whole star means Q star, P star is equal to 0, but Q star is Q, P star is P means QP is 0. Thus PQ is 0 if and only if QP is 0. Therefore we need only to show that M is orthogonal to N if and only if PQ is 0. That's enough. Okay. So it is sufficient to show that M is orthogonal to N if and only if PQ is equal to 0. First suppose M is orthogonal to N. Let y belongs to n. Then y belongs to n means y is certainly orthogonal to m. Because now y is orthogonal to n implies y belongs to where? M per. Thus, we have considered y belongs to n and y belongs to m per means n is contained in M pub. Okay. Now let z belongs to h be arbitrary. If z belongs to h is arbitrary, then what will happen? Q of z certainly belongs to range of q. Okay, this is by definition. This implies qz belongs to, what is the range of q? Range of q is we have taken to be n. So range of q means q of z belongs to n. This implies q, but n is contained in M per, accordingly q of z belongs to M per, which is the null space of P. This implies null, by definition P of qz must be equal to 0, or this implies Pq of z is equal to 0 for every z belongs to h. Now P into q of z is 0 for every z belongs to h means what you can declare? Pq itself is 0. P into q is 0. Conversely, suppose P into q is 0. Let x belongs to m and y belongs to n be arbitrary. Then P, by definition P of x is equal to x, q of y is equal to y. Therefore, we have inner product of x comma y is P of x comma q of y. So x comma P star q of y. So this is equal to x comma inner product x comma P star is P q of y. So this is equal to inner product of x comma pq is, just now we have shown, assume that pq is 0. So 0 of y means 0. Inner product of x comma 0 means 0. Thus x belongs to m, y belongs to n, and inner product of x comma y is 0 means what you can declare? M is orthogonal to n. Thus m is orthogonal to n if and only if p into q is 0. Okay. So these are the few results for this class. I will continue the other things in the next class. Thank you.